Thank you, Raimunda. I want to thank all the organizers for this great opportunity and a challenge to speak in front of Victor and Professor Makimoto and other great experts on Lie algebras. And I also want to apologize, and I also want to thank Victor from the beginning for creating this whole field, and it's certainly a fantastic field. And I want to apologize also in advance that this talk could have been prepared better, because of course I knew this conference was going to happen for a while, and there were these Lie algebras. I'm going to explain what they are, and I meant to investigate their precise relationship with Kac-Moody Lie algebras, and this somehow got postponed, and until now I started preparing this talk. I ran into some contradictions, so this is going to be a little bit rough. So in this sense, I'm not going to tell you what the contradictions are, but I'll tell you what I think is true. And then, so it all starts with a quiver. A quiver is a bunch of points and arrows. So a quiver, quiver Q, a quiver, something like this. So these are dots, and maybe I want an arrow. This orientation is not important, so I'm just not going to draw the orientation. So maybe 3 loops here, and what's my 1 loop here, and maybe 2 arrows here, something like this. And so, and the index I will be the set of vertices of this quiver. And to a quiver, equivalently, a quiver can be encoded by this generalized Cartan matrix, which is the rule for this. If you have loops, you put 2 minus twice the number of loops. So that would be minus 4 here, 0 here, and 2 here. And then there's a simple arrow here, and there is a double arrow here. And then 0, 0. And so I now want to go back to around 1980 when Victor published this just fantastic sequence of papers on relationship between quivers and representation theory. And in particular, he considered the following object, which is called Katz polynomial. So it's in the literature, in your paper, I think it's denoted M. In the literature, people denote it A, and well, I'm going to denote it K. So it depends on the quiver and the dimension vector. So V is in the set of dimension vectors. So dimension vectors. And so this is it's a polynomial of Q, and what this thing is you take representations of your quiver Q of dimension V. So representation of a quiver means you have these are the dimensions of the vector spaces, and for every arrow you give a linear operator. So it's a linear space on which, and you take those which are absolutely decomposable. And you take you quotient out by a group that naturally acts. So there's a group GV, which is the product of GLVI, and this you take as a set. That's extremely important. So what? As opposed to orbifold, as opposed to remembering what the stabilizer is. And you take this cardinality over a field with Q elements. What? Is a set, yes. Yeah, that's right. That's clear? And it's really crucial here that this you don't count the stabilizers. Was the first? I was curious. Did you ever know you don't want to count the stabilizer, or you tried that first, or? Yeah, well, you see, it's I wish I had this sort of vision to somehow, see things right from the beginning, and then I wouldn't be lost so many times. And so, so you see, somehow, if we have a quotient, the natural tendency is to count things with the weight which is 1 over the order of stabilizer, and you don't want to do this. You want to do this. And so then Victor formulated conjectures. So Victor's conjectures. And then first conjecture is that this is a polynomial. This is an element. It's a polynomial. An element. He proves it's a polynomial with integer coefficient, but as an element of, in fact, has non-negative integer coefficients. First conjecture. And the second conjecture, if Q has no loops, which this wouldn't be an example, but if there is no loops, then on the diagonal would be 2's, and so Kac-Moody algebra is defined, then the value of this polynomial at 0 equals the multiplicity of the root. So what I was going to say, of the root V for the GQ Kac-Moody. And so this conjecture has now been all proved, and well, I'm certainly not the person to survey this development, but by the work of the remarkable work of a great many very talented mathematicians. So what I was going to talk about is a question which is well, maybe I'm not going to write it down since there's no room on the board, but Victor also raises a question. So what about the other coefficients, and what about quivers with loops? And again, this is as I said, there's a whole machinery now of how to think about this, and maybe other people have other point of view on this, but I'm going to present the point of view well, I'm going to present the point of view that I was going to present. So, so towards answering this question of Victor, what does it mean in the most general situation? But before we go there, it may be useful to have an example in mind. So it's an example. Consider an affine quiver of type something like this, A3 hat. So A3 hat is a quiver which, well, now this is going to be hard because it's the hardest question of all of Lie theory is how many vertices in A3 hat, and I think it has 4 vertices. And let the dimension vector be the affine root, this one. Then what is Katz's polynomial for this? So maybe A3 hat. Just to do an example, what is this? Well, they're all one-dimensional, so it's just a bunch of numbers, bunch of maps are just numbers. If the numbers all non-zero, then their product along the circle is the invariant, and there's will be q minus 1 of this, right? Because there's non-zero. There's so many non-zero, so many non-zero elements here. Or the product could be 0, in which case it means that the condition that this is absolutely decomposable means the 0. There's only one 0. 0 sits somewhere here. Maybe one of these guys is 0. And then the rest is just a vector here, goes there, that's it. That's the only invariant. And so the 0, in how many places can the 0 be? Well, the 0, if this 3 is equals n, as I said, the hardest question in Lie theory is that there will be n plus 1 choice here. Right? So altogether it's q plus n. And then more generally, any multiple of this you can analyze similarly is also equal q plus n. And so we evaluate it in 0, when indeed we get, so evaluate this n hat k delta at 0, we get n, which is indeed the multiplicity, you get the Kac-Moody Lie algebra, which is SLN plus 1 hat, and you take the weight space, which is K delta, dimension of that. And now already in this example, I can illustrate. This might sound completely silly, but from many perspectives, the Lie algebra GLN hat is better Lie algebra than SLN hat. And if I look at the multiplicity of GLN plus 1 hat, multiplicity of a fine root here, well, this would be n plus 1, clearly. And which is the value of the Kac polynomial at 1. So the Lie algebras I'm going to discuss today, they have the property, so I'm going back to the beginning of this talk, that instead of evaluating at 0, you evaluate at 1. And there's something finer, in fact, is true. And why would you like, this algebra has some advantages, some disadvantages, was obviously not finely generated. So in some sense, if you like finely generated Lie algebras. On the other hand, if you think of this quiver, on the other hand, if you think, one of the simple reasons why you might like GLN over SLN is that if you can write the quiver in hat as, now I have to somehow think about my indices. Well, I'm going to write, doesn't matter. You can write as a quotient of an infinite quiver by a group of translation, which translates everything by, so to speak, n plus 1 steps. Okay? And then if you'd like some universal relation between quivers and affine Lie algebras, you might want to say that what I'd really like to associate is like some my G. Well, in this case, I know it's GLN plus 1 hat. Well, this really is what I associate to this quiver. This is centrally extended GL infinity, and I take invariance of that same action by Z. Right? It's very well known that just if you think of a GLN hat, you can think of this as infinite periodic matrices with the central extension being the standard central extension here. But more importantly, there are geometric reasons to like this slightly bigger Lie algebras better than these smaller. All right. So what are these varieties I want to talk about? So what I'd like to explain is what's a Nakajima variety. And this I'll explain in 2 steps. First, I explain the notion of a double quiver. That's a very simple notion. And that if you have a quiver such as this one, for example, its double is when you add, so suppose it's oriented. For this it's convenient to think of this as oriented. What you do is you add an arrow going for every arrow you add an arrow going in the opposite direction. So for every matrix you put a transpose matrix. This makes the representation of the double quiver to be the cotangent space of the representations of your original quiver, right? Because the dual two matrices are the transpose matrices by the trace pairing. And so, and if you want to take the cotangent, space, cotangent of something like this, cotangent of the quotient, you don't. So if you want to take the cotangent of the quotient, then, so if I want to take the rep q by GD, you don't quotient the cotangent space. You take cotangent bundle of quotient. You have to do two things. You take this on this. GV acts preserving the natural symplectic form. And so there is a moment map. Hence there's an algebraic. Hence there is this algebraic moment map. It's not mu. So you take the mu inverse of 0, and then you take the quotient. And so why is this? How to see that this is going to be extremely the notion that this is a set here and not the orbifold is going to be extremely tied up with the fact that, in fact, secretly one wants to consider the double quivers, is because the fiber over a representation, we would have a representation of original quiver, is here. What is it? It's the space. Oh, well, I'm going to write cardinality, so I'm really interested in cardinality, so I'll write the cardinality. Cardinality of the fiber is, well, it's the number of points in X1 between R and R. It's what the cotangent space is. And then the point is that this by Riemann-Roch, so this R here. So by Riemann-Roch, this thing is equal to some fixed power of Q, some fixed which always depends on dimension vector, and then X0, RR. And so then this is, and now if R is absolutely decomposable, then this means these are all linear transformations that commute with my representation. If it's absolutely decomposable, then invertible ones are. So this is a. Well, I'll just write a formula. You'll see why it's true. So if I want, there's the difference between invertible ones and non-invertible is just Q minus 1, and Q minus 1 is anyway eaten because there's a multiplicative group that acts trivially there. So inside of here, inside of this, is the multiplicative group of a field, acts trivially. And so we might as well quotient out by that. And so this would be this times the order of a stabilizer of R. So the order of the stabilizer in GV mod GM of R. And so you see when Victor wrote down that, he secretly wanted to count things in this double quiver and not in the original representation, because this is the weight with which you really count things there. And this says, well, I'm really counting points in the double quiver variety, not the region. And so this variety, which is much more interesting. This sort of varieties are much more interesting than the representation of quivers themselves. This really where geometry is happening. And so, and now we, it's some fixed thing. In Riemann-Roch will tell you that dimension of this minus dimension of that is something, which is some quadratic expression in V, yeah, which I don't remember. And so, so now we're going to talk the Nakajima varieties, and these are. So now we talk about framed double quiver. And these are considered by Nakajima. And so what this is, well, I continue with that example there. So I had a quiver, which was what? Was this quiver? And then this has dimension maybe v1 and v2. First, one introduces framing, means one takes a separate vector spaces of dimension, and the fact that they're separate, I'll indicate instead of dots, I'll put squares. Something of dimension w1, something of dimension w2, and then you take a framing map. It's like your quiver representation, only you also give a separate vector space and a map to your quiver representation. That's what's called framing. And now you double that. So we've, what color did I use? Well, that's unfortunate. And now we double, well, I use blue now. And now we double this, so this is and so one considers this Nakajima variety, VW, which I morally write, meaning that you have to understand this moment map business there, but I'll write it like this. So it's a T star of representation of this Q framed modulo GV. And then the remaining group, which is GW, which is the product of GLWI, this acts on this. But by this, I mean this moment map thing there. These are really remarkable varieties. This include, for affine quivers, i.e. A hat, sorry, D hat, E hat. These are modulo of sheaves. On AD surfaces. In particular, if I take the Nakajima variety corresponding to A0 hat, where A0 hat is the quiver with one loop, and I take it in dimension vector, I don't know, n and 1, this is my V and this is my W, that this is the Hilbert scheme. Of points in the surface A0, which is just C2. That's an example. And so these objects are of primary interest in the kind of thing that in the kind of question related with ordinary cohomology or K-theory of these varieties are of primary interest in four-dimensional gauge theories of the kind of that Sasha discussed in his lectures. And then the quantum cohomology of these objects or quantum K-theory of these objects are of great interest in things that live higher up, and which in Donaldson-Thomas, for example, in Donaldson-Thomas theory of threefolds, I don't want to talk about this here. It's a whole world in itself. So I'm not. But anyway, these are varieties of remarkable beauty and geometric interest. And what Nakajima constructed is you define, so then you also, you can define, so and define MV to be just disjoint union over all MW, I apologize, over all V, this M VW. Over the framing vector you fix and the dimension vector you add over. Like, for example, here you'd think one will be fixed and you sum over, you take the union over all Hilbert scheme of any number of points. And then what Nakajima constructed, an action of UQ of the loop of the G Kac-Moody, GQ Kac-Moody on if you have a Kac-Moody Lie algebra, you can define what the loop UQ of loop of that is. It's by itself not a generally speaking, not a Kac-Moody Lie algebra. This acts on the current K theory of the spaces. And in particular, the Lie algebra itself acts, acts on cohomology. So while immensely beautiful, these things are not quite cover the geometric applications one has in mind, because the operators that one really needs from geometric perspective, such as operators of quantum multiplication, those are the operators that Edik discussed in his lecture in some form. In this case, they are not contained in here. So Edik discussed the situation when this quiver was of finite type, and then there will be no difference between the Kac-Moody Lie algebra and this Lie algebra we're trying to discuss. But as long as you're outside of finite type, there is a difference, and geometrically interesting operators do not sit in here. And in fact, Nakajima himself constructed, for the Hilbert scheme of points, he constructed the action. So Nakajima himself, for the himself constructed the action of GLN plus 1 hat on the cohomology of Hilbert scheme, of Hilbert schemes of A surfaces. And this is not a specialization of this construction, it's a separate construction. And so in general, one needs a bigger algebra, and this is what I want to discuss. So now I come to the point where I'm going to say something about our joint work with Davesh. So with Davesh Malik, we start from the obvious observation that the following observation is an obvious observation that if I take Nakajima variety for some framing vector W, and I take direct product with the Nakajima variety with some other framing vector, which I call the W prime, this equals the fixed point set, and if I double the dimension vectors, and then with respect to some C star. Well, I apologize. I've sometimes write the multiplicative group of the field, sometimes write C star. Well, I don't know. We call A, where A is GM. And what is this action? So So this is an obvious thing. So this says, so how is this going to act? What's GW? This where A this sits inside the subgroup in GW. What's GW? GW have to give you this GW. After all, it's a product of GL, maybe GW1 plus W2. It's a product of GWI plus WI prime. And inside here, I'll give you a collection which is just a matrix Z W so many times, and then one WI prime many times. So this is where my Z in A goes. See, this is here I've the point with having this framing action is that if I act by a subgroup like this, then this forces, if I change my framing on some part of W by Z and by nothing on some other part, this forces the Q representation to become direct sum. So this is the locus of direct sum. Direct sums of representation. Yeah.
But that equality, on one side you have a natural action of GW plus GW prime, and the other one you have a natural action of GW plus W prime.
Well, on a fixed locus, you look at the centralizer, and the centralizer is just product, right? Yeah. Is that clear? So if I have a is that obvious? If I have a map and I can undo, just that something is fixed means I can undo this automorphism undo this change of framing by automorphism. This means that if I look at the eigenvalue decomposition of this automorphism, means it forces me to be direct sum. And so in situation like this, there's a rather abstract map. So in situations. In such situations, we have non-trivial canonical or non-trivial canonical maps that depends on certain choices, of which I will collide only two choices. I'm going to call it, so to speak, plus and minus. Stuff plus minus, this is going to be a map from the K-theory of the fixed locus to the K-theory of the ambient space. So it's going to go K of M V tensor K, so it's an equivalent K-theory. K of M W prime. Going to go also equivalent. I'll leave some space here. Goes to K equivalent theory of the polygon. And now, Raymond, your question would be in order because there's more group action on one side than on the other. So here, I'd like to then therefore tensor up as polynomials. Let's label Q coefficient. That's the K theory. That's to remember the K theory of the group that's gone. And this, I'm not going to discuss how these maps are constructed, but these maps that go wrong way. In K theory, you have pullback. This is some form of push forward, and that's canonical up to certain discrete choices. In particular, there are fundamental choices between plus and minus, between Z and Z inverse. So, and then what you get from this form R, maybe I'll write it, so to speak, K theoretical matrix of Z to be the ratio of the two. Sub minus inverse composed sub plus. That's an endomorphism of K tensor K, so to speak, tensor rational functions of Q. And the point about this canonicity of these maps is that this solves the quantum universe equation. Baxter. And so, since this is an operator in the tensor product, you can ask for the operators to act in triple product. Well, maybe I'll write it down. What this equation is. But if I now take the K theory, well, I abbreviate, W1 tensor W2 tensor K3 of W3, then the equation will take, if I take the R, the operator in the first two with parameter, which is the ratio of this, times first and third, second and third, and then you get the other way around. And so then by Faddeev-Rechtin Tahtajan gives an action of UQ of loops in some Lie algebra G. And now I would like to discuss what this Lie algebra G is. So how do we know what this Lie algebra G is? So maybe I'll say one word about words somehow. How is that related to some things that got mentioned in ethics talk? Is that there was a conjecture by some aspects of this are still remaining conjecture, but the bulk of the conjecture I think is proven that there was a conjecture by Nekrasov-Svidashvili to the effect that quantum cohomology of these Nakajima varieties is a quantum integrable system of so to speak Young-Baxter type. And this construction what this construction recovers is that R matrix from which you get the integrals of motion and so on and so forth. And so to know what this Lie algebra is, one way to see it is to, if I can find it in my notes, is to where I'm in my notes. Maybe I'm here. So is to look into homology. This K-theoretic R matrix degenerates to a rational R matrix. It's rational. Where U is now, instead of being element in the group, it's in the Lie algebra of that torus. Where Z was sitting in the torus itself, and U is an element in the Lie algebra. And then this R matrix, this cohomological R matrix, RU, is of the form 1 plus, there's some deformation parameter H bar over U times the classical R matrix. And this classical R matrix has the sum is the form of summation hi tensor hi upper I plus summation E alpha tensor E upper alpha, where this alpha non-zero, where this ranges over root spaces of this Lie algebra G. Once you have a solution of the classical Young-Baxter equation, you can reconstruct from it a Lie algebra, and that's the Lie algebra that sits here. And so what this Lie algebra is in examples is for example, for the quiver for affine quivers, you only depart just a little bit. You have quiver for the quiver which is AN hat. This Lie algebra G is GLN plus 1 hat. And the way it acts in the so if your quantum loop group was acting in K theory, the original algebra just acts in cohomology. And the way it acts is, well, I'm just going to remind Nakajima's construction. And so this acts on the cohomology, on the covariant cohomology of the Hilbert scheme. Say, for example, the Hilbert scheme of AN surface. What's an AN surface look like? So AN surface is a surface sort of, say maybe this would be an example of A4 surface or A3 surface. And inside of the A3 surface, there are these exceptional curves. There are 3 of them. And if I look at my G, if I look in dimension K delta, this is spanned by this Nakajima operators. This is, so to speak, alpha minus K of gamma I, or this range over this curve. So if I have a curve in the surface, so these are the so you know A3 surface is a resolution of singularity, and the exceptional locus of the singularity is, in this case, 3 curves. And if I have, or maybe I'll denote them gamma 1, gamma 2, or maybe I'll denote them, since they're exceptional curves, I denote them EI. EI. And that, so if I have my exceptional curves are E1, E2, E3, and then the operator, if I have an operator alpha minus K, what it does, it's the Hilbert scheme of points parameterizes a bunch of points in the surface. So this AK of A2 ends some kind of big fat K-fold point. So this is with multiplicity K. And this is what this operator A minus K of E2 does. But also there is Nakajima operator. These guys belong to the SL part. But also there's operator which is A alpha minus K of 1, which just acts just the same, but adds the point anywhere it wants. So instead also here is alpha minus K of 1 of the fundamental class. That's an also geometric operator. You have a bunch of points. You can add a K-fold stuff somewhere in the surface. That's somehow. And so what's the dimension of this cycle? Let's say, so if I take, so this is. So this dimension of the cycle created by alpha minus K of EI what is it? So if in the Hilbert scheme of points, I look at schemes which have fatness k, then it's a classical result. There'll be k minus 1 is this dimension. This is the dimension. This is the dimension of the punctual of the what's called the punctual Hilbert scheme. Means all points sits in the same place. Like for example, if you have 2 points, and when 2 points come together in Hilbert scheme, you remember the direction by which I came, and that direction gives you 1 degree of freedom. And then plus 1 for this is the dimension of where this happens. And so this is therefore k, which is the dimension which is equals which is the middle dimension of the Hilbert scheme of k points over 2. So it's a middle dimensional thing. But if I look at the dimension of alpha minus k of 1, this is the same computation, k minus 1 plus now 2, because that's the dimension of the surface. And so I get middle plus 1. And so compare with, so if I count my elements in the Lie algebra by this homological dimension, I get n for this, n of this, for an, and 1 of this for an. And now we're supposed to compare this with the Katz polynomial. So now I realized I've been denoting, there was a certain mistake in denoting Katz polynomial by k, because you can't tell whether it's k theory or Katz polynomial. But I guess the things are almost congruent. So it's yeah, right. That'll be some fancy field. So anyway, so on the other hand, the Katz polynomial, maybe I'll write just like this. Katz polynomial of this an head quiver in dimension vector k delta, it was q plus n. Right? Because this q is then, this q corresponds to this, and n corresponds to that. Some other color. And so what I think is true in general, which although, like I said, I think is true in general, is that so in general, G, my G has a double grading, so it has a Cartan part plus G alpha, where alpha not 0. And then this further, so this is the grading by the roots, and maybe further refined, can be further refined by cohomological degree. So it'd be G, again, H was all in cohomological degree 0, it's not so interesting. And then you take alpha non-zero, and then K in Z, you look at G alpha K. And so what I think is true is that, somehow that if I take this generating function, if I take sum, this Katz polynomial of some dimension alpha of Q is summation Q to the K. This is cohomological degree counting from the middle. And then Q to the K dimension G alpha K. Then you can somehow try to talk more about it, but as I said, in preparing this talk, I've been running into certain inconsistencies in my logic, so maybe the less I say, the better. And then, especially since this is being recorded. So incidentally, I profoundly apologize to all speakers whose talks I missed because of scratching my head, somehow trying to see whether this holds water. I mean, whether there's actual argument or it's just thinking. So yeah, maybe I'll. Right, I didn't say anything about why it is important to consider these big Lie algebras. Well, you can say it like this. You can say that even though they're infinitely generated, so this somehow, if you dislike infinitely generated Lie algebras, then what can I say? But if you ask for maybe I'll say it like this. So there's a theorem we prove with Davish, and that says that this quantum connection in quantum homology there is something called quantum connection, which for Nakajima varieties, well, equals something called Casimir connection. For this G, where the Casimir connection, I'm not going to write the whole thing in it, but its typical term in this Casimir connection looks something like this. There's a summation Z alpha 1 minus Z alpha E minus alpha E alpha, something like this, and then there's an inner product with something like this. And so since you really do need all these root generators there, so you can't get away with the small Lie algebras if you just, I mean, if you want to describe quantum cohomology, then just you have to consider that. Otherwise, there's just no, yeah. Well, it's just exactly the Lie algebra you need, and so right, and maybe here I'll stop.